Okay, well, this is what we're talking about, functions as transformations, specifically linear functions. This is the way I would like to explain it right here, what it means to have a transformation. So a function between two Euclidean spaces, dimension n and dimension m, that they do not have to match. The function takes the domain, which is equal to one Euclidean space, transforms it somehow, but in a linear fashion, and then places the result within the codomain. Okay, so starting with the that's at the top I just added, in addition to example 1, example 2, we considered previously. Now I have example 0, which is pretty much what happened in pre-calculus, calculus, and pre-calculus. Okay, so as you can see, both domain and codomain are one-dimensional. Okay, 1 and 1. So you can think about, once again, if this is my x-axis, it is somehow transformed into the y-axis. So, as you can see, it can happen in a number of ways, but since we only do stretching, shrinking, this is what you're used to see, x-axis, y-axis. But really, if you want to think about the graph, that's where the graph is here somewhere. But if you want to think about transformation, then there is really no particular relation between them. You put them on perpendicular axes for a function in order to visualize it. But if we want to think in terms of transformations, so that we don't have to put all the dimensions together on one piece of paper, we can't in higher dimensions. Then, like I said, these two exist separate lines. They leave separate lines. So the x-axis, the y-axis, and then the function is transformed this into that. And with linear functions, it's not that complicated. So, like I said, you can first transform it by shrinking or stretching, and then you place it within the y-axis. Okay. What else can happen? I can also flip it. Okay, so these are two basic things that can happen. There aren't too many linear functions. So stretching, shrinking, stretching, flipping, and once again, remember, you can end up with like this, nothing but a point, so a constant function. Okay, and then what I talked about last time, it is example number 1 is the line. The domain is the x-axis or t-axis. Okay, then it is placed not necessarily within one dimension anymore, but could be two-dimensional, which could be a plane. Okay, so you place your straight line in some way within the plane. So that's a one-dimensional linear function. You can now flipping now is not flipping like that. It is rotation, as a matter of fact. So infinitely many possibilities. And there is still as you can see over there, the degenerate case. This is the degenerate case when nothing but 0, 1 producing 1 point and nothing more. Now, example number 2, functions of two variables, everything is flipped. So now, this is my domain. This is my domain xy plane, for example, and then I'm supposed to somehow place it within the R, the codomain. Okay, so I could still totally contract it to a point, but the typical situation is to try to roll one into the other. So as you can see, there are two degenerate cases. One is when the whole plane is, well, so this is the most degenerate case. So you take the whole plane and you place it within the within the axis, within the output, as a single point. So that is your output. That is the degenerate case. So the image, it is possible, is only 1 point. Okay, so that's the most degenerate case. There is, however, not entirely degenerate case, even though we're losing a lot of stuff here. So we made a line from a plane, how we roll it around the axis. Yeah. Okay, so in other words, that was the example of a linear function right here. F of xy is equal to x, or is equal to y, doesn't matter. But you can see how two-dimensional input produces one-dimensional output. Okay, so once again, in the former case, the graph is a straight line. I'm sorry, the image rather is a straight line, and the graph too. In the latter case, the graph is a plane, but that's not what we're talking about here. We try to think step away from graphs or even images and think about transformations. And yeah.
What is written there? Place it.
What?
Place it.
And places F. So the word, the noun is F, the function. Okay?
Takes the domain,
Takes the domain Rn, transforms it, comma, and places it within the codomain Rm.
What's Rn exactly?
This is where, this is where they are. Domain and codomain, input, output. So you transform one into the other, that's all. Okay, so, and now we are finally getting to why we have been doing this. This has been a build-up pretty much towards this. R2 to R2. Okay, so that's really the most interesting case. So you take a plane, two-dimensional input, space of inputs is two-dimensional, and you place it within another two-dimensional space. Okay, so the possibilities are very extreme. For example, you can still you can rotate it, you can flip it. Okay, you can shrink it disproportionately in different directions, and there are still degenerate cases, such as this is still a possibility. You can take the plane, shrink, roll it, and then place it. So that's still a possibility. And this is also still a possibility. So you can put it like this. So there are two degenerate cases because there's so much room. Then we have three cases. So image, the worst case is 0. Image is a line, and image is the plane. So the whole thing. So these are the only three possibilities. Case 1, case 2, case 3. So in the two previous examples, only one degenerate case. One was to worry about when everything collapses to 0. And here we have a kind of a semi-degenerate case like this. So we collapse it, but not entirely, but we take that plane and turn it into a line, and then that's not the worst thing that you can think of. Do you remember why we care about this case? What is so special about it?
Case 3.
What?
Case 3.
No. That's example 3. It refers to functions when the domain and codomain are both two-dimensional. So the examples that we just saw was lines from one-dimensional to two-dimensional, functions of two variables from two-dimensional to one-dimensional, and now we have the next one, which does not have a special name, from two-dimensional to two-dimensional. Remember when we saw it? First day of classes? No? Remember we solved the system of linear equations, and it had two variables. Okay, so that's exactly what we're talking about. And so since we were going to start over with that, so we'll do next that system and build all the way up to see that function over here and see why that will explain why we care. But before I do that, I want to do one more table. So R1, R2, R3, R4, and here, so this is the domain. And all of these functions are possible. So this is, these are lines. So these are lines. Domain is one-dimensional. Codomain is any. Okay, so that's example 1. Example 2 that we talked about is this. This one. That's the plane. And now finally, this is every arrow is possible. So whichever you pick on the left and another on the right, they all make sense, and they have their own importance. And so and all the way. So this is Rn and Rm, as I talked about. So this is our primary interest at this point, from R2 to R2. So input is a two-dimensional vector. Output is a two-dimensional vector. Okay. Well, I'm not gonna. Long story short, they all function from Rn to Rm is given by a matrix m by n. Okay, so every linear function is given by a matrix, and only the dimensions of the matrix is what we care about. So if we know the dimensions of the domain and codomain, we know the dimensions of the matrix, which is kind of a weird coincidence of that we use the same word for dimensions of the two spaces and dimensions of the matrix, but they exactly coincide. So matrix with dimensions n and m, and the dimensions of the domain codomain are also n and m. Okay, so that's a long story in perspective, but we are looking at that red arrow over there, so we're going to be, initially at least, we're going to be looking at 2x2 matrices. Okay, so that's fairly straightforward. So, okay, so let's get started with that example. Once again, so going all the way back to the first day, so we have, it's a mixture problem. We have two types of coffee. Whatever, there was a Kenyan coffee and a Colombian. I don't think I spelled it right. So this one is $2 per pound. So let's just start over and all the way, repeat it from the beginning. And Colombian is $3 per pound. Okay, and then we have, the question is how much of each? We need to produce 6 pounds of blend worth $14. Okay, so just remember, as I made that point earlier, last time, is that if this sounds a little bit frivolous or kind of a toy example, it is a toy example, but behind it, any kind of mixture problem that you might face, once again, portfolios, you want to mix the different stocks and bonds in your portfolio, and then you're looking for some perfect allotment of different instruments. Okay, so then instead of have two variables, you'll have more variables, and that's why you need matrices of higher dimensions. But let's go all the way through. So you might remember. So we went through this. So that's the problem. Now solution is to let x be the amount of Kenyan coffee in the blend, and y be the amount of Colombian coffee in the blend. Okay, then the two statements that we have, the two statements are hidden inside of the question, and which is 6 pounds. So it means that 6 pounds of blend. 6 pounds of blend. So that's I write it here, and what do I get it? I'm getting x plus y is equal to 6. the blend altogether is weighs 6 pounds. And then the second one is it is worth $14. Okay, so that produces the second equation, which is what? 2x plus 3y, yeah. 2x plus 3y is equal to 14. So once again, technically we call this a system of linear equations. A system meaning that we have two variables and two equations. Both of the equations have to be satisfied in order for us to call that xy a solution. Okay, so to solve means to find all pairs xy that satisfy both equations. Okay, at this point, before we proceed to algebra, let's quickly look at the geometry. The two equations, geometrically, what do they represent?
Lines.
What?
Lines.
They're lines. So both equations represent lines on the xy plane. And then the solution is their intersection. So generally speaking, any two equations put together like that, linear equations, could constitute a system of linear equations, and therefore any geometric, any two lines, whatever their relation to each other, might correspond to that equation. So which means that the solution might be whatever can happen to two straight lines will happen to some system of linear equations. So for example, they could intersect. That's the generic case. Another generic case, non-generic case, is when they do not intersect. They're parallel. Okay, no solution. And the third one, it's the same line, so infinitely many solutions. So these are the three possibilities. We will get back to that, but right now we're exploring the algebraic angle, and we want to see where here there is that function, linear function of two variables from R2 to R2. Okay, so what we do is we start writing this in a more consistent way, like this. So I extract the coefficients, and I align the variables one under the other. So as you can see, y's lie one under the other, and coefficients lie one under the other, and the free terms are on the right, also separate. Okay, so and then at this point, what I do is I start from vectors. So this is how well, so far these are the vectors. So far these are vectors, 2 by 2, or rather two-dimensional vectors that we can see. Right there. There are just two equations. Then if two numbers are one under the other, you can say, hopefully it means something, that they form vectors. So I can see three vectors here already. Okay? So then the idea is make the system into a single vector equation. So where is the vector equation with respect to these vectors? 1, 2, 1, 3, 6, 14. We're not going to solve this equation. It doesn't really matter. So where's the equation with respect to these three vectors?
First one times x plus the second one
Right,
times y.
right. So we simply multiply, x serves as a multiple, as a constant multiple that vector is multiplied by. So like this, that's all. So you can certainly, it is actually the challenge, this is the challenge, that the step that we made. Backwards is easy. Why? I just, I put the, I know the algebra vectors. I know that all algebra vectors is component-wise, which means that I look at one component at a time, and then every equation, either one of the equations will be the component of my vectors. So let's carry that out. So it's easy, but let's do it anyway. So vector algebra, component-wise, I have 1 times x plus 1 times y. Okay, so that's addition in the left-hand side. Here I have 2 times x plus 3 times y. So that is my vector on the left, and on the right I have 6, 14. Okay, so I just carry out my algebra component-wise. And then what I know about vectors, the two vectors are equal to each other whenever both of their components equal. Okay, so that's how I arrive back to my equations. So two equations, each corresponds to either x component, and the other one corresponds to y component. So forget about x and y inside of the equations themselves. That's not what I'm talking about. I'm talking about the xy components of these vectors. That we just formed, 1, 2, 1, 3, and 6, 14. You don't have to call them xy necessarily. You can say one is the first coordinate, or first component, second component. Okay, but we used to usually call them x and y components in the two-dimensional case. And then we have this equation. So that is a vector equation. It is a progress, and let's step before we move on, and let's try to interpret what this means. Let me try to let's try to understand. Let's try to understand what we're looking at. The equation geometrically. So geometry of this equation. The geometry of this equation. So I'm doing it on the xy plane. Okay. Let me plot these two vectors. So I'll have 1, 2, 1, 2, like this, maybe. Just a minute. 1, 2. This is my vector. 1, 2. 1, 2. Okay, and the second is 1, 3. Okay. Let me make it slightly slower like this. So this is 1, 2, and I have a 1, 3. 1, 3. Okay, these are the two vectors. And then there is the third vector, which is 6, 14. 6, 14. So this is 1, so 6, and 14, I don't know how far it goes. Well, it's pretty far. 8, well, here maybe.
Could you do
What?
3 over 7 to kind of get the same idea? Or no?
No, I just want to take what we actually see here. It might be awkward, but I think I can make that point. So this is a big vector. I actually can see this is 6, 14 vector right there. This is my 6, 14 vector. It goes pretty far, but that's okay. And now you see, so these are the three vectors that we see in our vector equation. I plotted them, and now what is the meaning of x and y? That x and y are the ones that we're looking for, right? So what is that? What we're trying to accomplish here?
It's like some stretch of 1, 2 plus some stretch of 1, 2.
That's right. That's right. So multiples are stretches. So I stretch the first vector, right? So stretch by x, by factor of x, and this is also stretch by factor of y, okay? And then they're supposed to produce this vector, the blue vector, the long one. Okay, so that's the solution, that's what we're trying to accomplish. It is because of the vector is kind of awkward, and then it might be hard to actually see it. Well, let's pick a simpler equation. There's just as an illustration of what can something more reasonable that we might face. Say I have a 2, 1 here, and I have 1, 3 there, 1, 3 there. And then we are creating what is called a linear combination. A linear combination is simply taking the two multiples and add them together. Okay, so in other words, I multiply one by something and the other one by something. So for example, I could multiply the first one by 3, maybe like this. Okay, and then multiply the other one by, how about 2? Okay, and then what I produce, we remember this picture when we talked about especially distributive property. So as you can see, we're starting with 1, 3, the green one, and 2, 1, the orange one, and by multiplying the first one by 3, so it is twice 2 times 1, 2, 1, and this is, I'm sorry, 3 times, and this is twice 1, 3. And then we add them together, producing the vector, this vector. Okay, so imagine that was our problem. The same, it's just the picture is slightly easier to comprehend, but the problem we're trying to solve is exactly the same. Represent the blue vector as a linear combination of those two vectors, as the sum of multiples of the other two vectors. That's what linear combination is. Sum of two multiples. Okay, so that's the insight that vector algebra provides us with. So we're dealing with vectors, and well, if now we're trying to let's remember what these vectors. Do you remember what the vectors stand for? The first two vectors. It might easy to forget, but actually it is quite insightful that the first vector is entirely about the Kenyan coffee, and the second was entirely about the Colombian coffee. So instead of combining things like horizontally, meaning one equation was about, remember we had two equations. One equation was about the weight, and the other one was about the price. So that was how we combine things. Now we're combining them like this, vector-wise. So we combine in vector the two types of coffee. Two types of coffee are the ones that the quantities rather are. So the involvement of, say, Kenyan coffee is 1 and 2. It is involved as 1 in the weight, and it is involved with 2 in the price. Similarly, 1 is the weight of the Colombian coffee, and 3 is its price. Okay, and 614 is then the price of the blend. So once again, these 3 vectors that we have discovered are Kenyan coffee, Colombian coffee, and the blend. Okay, so you see how it works out. So combining 2 or maybe more under different circumstances of different components, stocks or whatever, and then into a blend. So it is the problems of this kind are called mixture problems, and they could be mixtures of anything, including something man-made. Okay, so the picture on the right is just a more comfortable picture of how what we're trying to solve. We can represent our blue vector as a linear combination of those two, orange and green. Okay, but really it is just what we're trying to accomplish, and we would have stopped here. We are past that. We are past that situation. We are now looking for more, and a vector equation doesn't do it for us once we realize that x and y, so that's a big step, but x and y, what do they form?
Which x and y are you talking
No, those x and y in the equation. No. They form another vector. So as you can see, we already formed 3 vectors, right? And then, wait a minute, we have x and y, and then why not to put it in a vector form too? Once again, the logic is the same. So what if we are not doing mixture of 2, we make a mixture of 3 or 100? So then let's just as well put it in the one vector, and that will be the unknown vector. Just like in solving equations as before, but this time it's not. I don't want to have an equation with 2 unknowns, x and y. How about I have only 1 unknown? So instead of then finding x and y, we'll find xy. Okay, so x is xy. After all, remember that, put a question mark here, so that's what we're supposed to find. Remember that was the original statement of our problem right here. To solve the system, find all pairs x, y that satisfy both equations. What is a pair if not just a 2-dimensional vector? So a pair, certainly it was initially we thought of x and y as a point. Remember when we talked about straight lines, how they intersect or not, we thought of them as points in the plane. But now vector point of view is more is better, and so we form yet one more vector. It is just the big deal now becomes how do we incorporate that idea into our equation? Where is the vector? Where is the vector in that? Where is the vector xy in our equation? What?
Isn't it the resultant vector?
Resulting?
Resultant, the blue one?
Well, no, xy is made of those x and y, is the unknown numbers x and y. It is what we're supposed to find, and they are the ones here. So this, if we are still here, the question was, then the problem was solve for xy. So that was the where we were just a few minutes ago, but now we're past that. And we're not solving for xy, but we're solving for a vector xy, except we don't have the equation with respect to xy yet. So once again, we have to take a careful look at this equation and recognize how vector xy comes into play. So do you see it yet?
Multiply by the 2 by 2.
Which one?
Like you make a matrix, it's like 1, 1, 2, 3 multiplied by big X.
That's right. And the
Dot product?
in the dot product, right. So in other words, that's what we're looking at is look at the top. Actually, we can go all the way back to the equation and ask ourselves what's the meaning of the first equation, the left-hand side of the first equation. The left-hand side of the first equation is, well, let me point that out. Hold on a second. It is the dot product. Okay, so let me write it out, and we'll see what we're talking about here. So so I want to have a vector xy, and as the input. Remember, we're talking about functions of two variables, and the output still should be my 6, 14. Okay, 6, 14. And indeed, what we produce here, the way to arrange those two vectors, 1, 2, and 1, 3, turns out that it's actually better to, rather than keep them as two separate vectors, we put them in the form of a matrix, a table. So it's a two columns of that vector, of that table. Yeah. Did I say columns? I meant rows. 1, 2, 1, 2, 1, 3. Let me, so this is the one, and this is the other one. Okay, so you can still see these two vectors on our picture, right? The orange one and the green one. So they are still the vectors, and we remember what they mean, right? They refer to the two types of coffee and how they participate in the whole picture. But you can see how we what we're doing here is this. This is, we recognize the dot product. Let me try to, so this is still the blue one, and let me go this way. Oops. Like this. Okay, so as you can see, we take the dot product of 1, 2, and xy. It is equal to 1 times x plus 2 times y, and that is supposed to be equal to 6. 6? Okay, so once again, if I take 1, 2 is the first column of our matrix. It is that vector that we started with, and 6 is the first entry on the right. Okay, so let me maybe copy and paste here. Okay, so let me demonstrate what I'm talking about. So the what at the top is the more compact form, but if I erase the irrelevant parts, it hopefully will be clear. Okay, 1, 2, and xy gives me 6. That is what we are looking at, is the first equation. The dot product of these two vectors, it just happens to be one is a row and the other one is a column, but if you start doing the dot product here, you will have 1 times x plus 2 times y, right? Now the second equation is this. The second equation, if we go all the way to the original, so I eliminate this. I still keep xy, and I'm left with 14 like this. Okay? So once again, the dot product 1, 3, and xy gives me 1 times x plus 3 times y, and it's supposed to give me 14.
I thought our equations were x plus 1 plus 6.
That's what I thought.
3y.
I thought I messed up some of the, what's the original equation? 2 plus 3. So over here it's 2, right? Right? Over here it's 2.
Yeah.
And then I messed it up over here as well.
Yeah, it should
Yeah,
be 1,
1,
1,
1.
2, 3.
They're supposed to be 2, which makes it even worse because they will just merge. 2 over here. Did I fix them all to
You just replaced 2, okay.
Yeah, that was a mistake. No, hold on a second. That's not right.
No, yeah, you should have just done 1, 1, and 2, 3.
I put, hold on a second. The equation is 1, 1, 2, 3.
Yeah.
2, 3, 2, 3. 2, 3. Okay, so this is okay. Is it?
Well,
It's 1, 1, 2.
yeah, sure, it's one.
1, 1, the top, so one more
So
correct.
you list them you list them horizontally, and you should list them vertically, like your vectors.
Right, so yeah, we are not flipping. We're not flipping. So these are the rows. These are the equations, as I said. So first, second. Okay, so the in our matrix, the first row. So the rows is what we concentrate on. So to match our matrix equation, which is what we're looking at right now, we match the rows of our matrix with the equations of our system. Okay, so the first equation was 1, 1, and the second was 2, 3, the coefficients that is. And then how do we combine those x, y's? How do we incorporate x and y into this? We do it through pretty much the dot product, one row at a time, right? So you see this, what I just wrote here. Is it clear what we're dealing with? So second equation. Okay, so that's how it works out. One row at a time and one entry at a time. So as you can see, to get that output, the two numbers, we have to carry out quite a bit of computation. So every number on the right, which is the output of our function, it takes a whole dot product to find. So well, let's now see that. Let me put it this way. That we know that this is the input. So if I input x, y, no, it is the input, yes. Input. Where's the output? This is the output. Okay, so the input is x, y. The output is 614. And finally, this is the function. So function, let's call it A, applied to input xy produces the output for 614. Okay, so let's call output B in order to write the equation in the form that is finally compact. So I have A times x is equal to b. Okay, so this is the equation. This is the why this all has been worth the effort, is that we are now able to compact equation with any number, any system of equations with any number of equations with any number of unknowns into a compact equation like this, where so these are two vectors and this is a matrix. And at this point, matrix is nothing but a table of numbers. Okay, so as you can see, it matches solving equations in dimension 1 with only one variable. And so 3x is equal to 5, x is equal to 5/3. Okay, so that's the, if we know how to solve equations with numbers, we should be able to figure out how to solve that equation that we have on the left. It certainly is way trickier because well, you can see how many numbers are involved. So if even now we have 4 numbers involved, but it is not entirely well. I think I have a minute left. I want you to see that a 2x2 matrix is really not, which is where we came from, is not entirely necessary. So here's an example. So this is example 3. This is example 3. Remember the 3 examples that we looked at were line, plane, and now this. Okay, so if we move backwards, example 2, we mentioned the dot product, right? Does this look familiar? It will be the equation of the plane. It just happens that the matrix is 1 by 2. So in the example here, we had a matrix 2 by 2. Two unknowns, two-dimensional input, two-dimensional input. And here, it just happens the matrix is not 2 by 2, and it is quite possible that it does not have to be a square matrix. It does not have to have any particular dimensions. So this is 1 by 2, and we simply multiply, and we have mx plus ny. Okay, so that's so a function from R2 to R. This one is a matrix. It's a function from R2 to R2. And we had example R2 to R as well as R to R2. So we'll do this one next time.